Good afternoon, everyone. Welcome to the robotics seminar. I know this also turns out to be the last edition or the last, talk of this semester. It's a pleasure to have Ashish Deshpande with us. Ashish is a professor in the mechanical engineering department at UT Austin. His lab has done some wonderful work on developing exoskeletons and also dexterous hands. Before Austin, Ashish got his PhD at University of Michigan in Ann Arbor, then spent a couple of years in UW, and then finally decided to move to Austin. It's a pleasure to have you, Ashish, and looking forward to your talk.
Thank you. Thank you. Thank you, Pulkit. It's a huge honor and distinct pleasure to be here. Thank you all for being here late on Friday. Today I'm going to talk about Harmony Exoskeleton, the picture you see here. I've limited my talk to this one robot we built. I will show some pictures of other robots, including robot hand. But if you have interest in that, we can talk at another time. This research began back in 2011 in my lab at UT Austin. By the way, before University of Washington, I was at University of Maine, kind of near here for 2 years, and then moved to 2011 to UT Austin. Over the years, we built multiple versions of this exoskeleton, developed control algorithms, and carried out testing with both healthy and stroke participants. 2 startups have spun out from this project, namely Harmonic Bionics and Contoro. And I'm excited to tell you about some of the technological advances as well as ongoing scientific discoveries that we are embarked upon with this robot. I should mention that currently I'm on leave from my academic position at UT and working with Meta Reality Lab, but all the work presented here is from my lab at UT Austin. Okay, before I jump into my talk, I would like to first acknowledge my team members. Any professor here would acknowledge none of what we do is possible without inspiration, efforts of researchers, grad students, undergrads in the lab. And I'm very fortunate to have worked with really smart and inspiring people. So here we are in front of our brand new robotics building. We'll talk about that a bit more. And here we are at one of our recent holiday parties. I would also like to thank my collaborators from around the world, and I will mention some of them as we go through the talk. I thought I will also, before jumping into main content, talk about Texas Robotics. It's a cross-disciplinary organization at UT Austin, my home institution. We are kind of still in our home department. There are 16 faculty members, though, who are under this robotics umbrella. Our core competencies are all kinds of robotics, but specifically long-term autonomy, human-robot interaction, and robot manipulation. We have researchers from mechanical, aerospace, electrical, computer science in the core faculty program. This is a glimpse into one picture of our new robotics building, which used to be an old gym that turned into a robotics building. So it has high ceiling and beautiful shared robotics place. I'm bringing that here to highlight this kind of new and growing area at UT Austin, and also to people who might be looking for faculty positions to come apply, because we have openings where we plan to go from 16 to close to 25 faculty in core robotics area. So reach out to me if you're interested. Okay, to the talk. Overall, I'm motivated to bring robots in close physical contact with humans to help improve quality of life. The big question that's at heart of my work is, can we cause changes in the internal state of a participant through physical interactions with the robot? To tackle this challenge, we need to go well beyond a robot moving the person's body passively, which itself is a challenging problem, because we need to redesign the robot from industrial setting to be safer human setting. But I'm thinking about seamless and continuous interaction such that an exoskeleton moves the body, affecting the motor behavior, that is your movement, your torque capabilities that you see outwardly. That could serve as a stimulation for the brain to update its own state, causing changes in behavior. Then further, exoskeleton updates its control response, and the virtual cycle continues. That's the vision. That's the vision of lots of rehab robotics labs. I think that towards this mission, we need to address 2 sets of questions, broadly speaking, robot design itself, and then algorithms and measurements for affecting the internal state. So these are sort of the 2 pillars that I'm focused on. Just sort of as a high-level motivation, if I can achieve this melding of body, mind, and machine, where movement of the body affected by robot that affects the brain state and sort of virtuous cycle continues, if you could do that, then it could be a game changer for a variety of applications, which, it's only limited by our imagination. I've listed a few just for fun. I want to highlight that focus of my lab is on the medical applications within that. And even within that, we are focused on hands and arms. So we are interested in robotic hands for improving prosthesis. We are interested in helping, where is my cursor? Helping people with spinal cord injury, how we can improve the quality of life, and interested in stroke rehabilitation. And today's focus for us is on stroke rehabilitation for upper body recovery. In my group, our approach is on sort of on the big picture is through the development of research platform. And I started with this because when I began my work, I felt that there wasn't the right platform to achieve this brain, body, and the machine melding. Today, I'm going to tell you a story about the Harmony exoskeleton as an illustrative example. And my claim is that the thought process, the approach, the technological and scientific advances have wider applicability. In fact, my group has been working on other systems, including a hand exoskeleton and end effectors along this vision. And I will bring up a short video of Maestro hand exoskeleton that you see in this picture toward the end if you get a chance. Okay, where are we? All right, let's set up the problem itself. And to get everybody on the same page, let's talk about stroke for a second. Many of you may know that, but that stroke is the leading cause of disability in the US and around the world. More than 800,000 new strokes happen each year in the US alone. That's a huge number. And that results in millions of people living with disabilities. Fortunately, more and more people are surviving after stroke. That area of care has really improved with some advances, which is great. But with the instances of stroke growing and fewer people dying, we have the number of stroke survivors growing. And this number is expected to keep growing, as this graph shows. This has resulted in severe costs at all levels: personal, family, societal, so on and so forth. And I'm motivated to build robotic tools to alleviate this huge societal problem. And I'm sure that some of you in this room may have had experience with strokes to family members and friends. Myself, for my grandmother suffered a number of disabilities before she passed away because of stroke. And my sister is an occupational therapist who sees stroke patients almost every day. So I want to help in that arena. Okay, so how do we do that? Before we do that, first we need to dive into the problem itself even further. So to get everybody on the same page, let me give you some high-level background. I can talk about this for a long time. Happy to do that separately. But at a high level, stroke happens when a blood vessel carrying oxygen or nutrients to the brain is either blocked or burst. Acute treatments have improved, as I was saying, resulting in more patients surviving a stroke. Still, stroke results in death of cells in the brain, resulting in disabilities typically on one side of the body. That many of you may know that. It's a paralysis, for example, on one side of the body. While stroke can present movement, speech, and cognitive disabilities, focus of my work is on movement recovery after stroke, and more specifically on recovery of arm and hand function. This is a critical problem because more than 80% of stroke survivors have some sort of arm or hand disability, and only less than 20% recover from that. Post-stroke rehabilitation, which consists of physical and occupational therapy, aims to overcome movement disabilities caused by stroke. And then the problem for us is, at the Robotics, is can we jump into that arena of post-stroke rehabilitation by using the robot to move the body in the hopes of either, going to use sort of colloquial term, rewiring the brain or having different neurons take over some of the functions. It's more complicated than that, but I just kind of at a high level, at least we can think of that as our problem, right? Let's think about a very specific example. I would like to introduce Mr. Avril Seal. I think that video is going to play up in a second. He's a colleague of mine at UT Austin. He suffered stroke 4 years ago that left him partially paralyzed on his right side. After more than 10 weeks of inpatient therapy, he learned to walk again, which is fantastic, but he was left with limited use of his right arm and hand. as you can see from this video. In this case, the therapist, you can barely see here, she's asking him to reach up with his arm. And this is his ability at this point even. While you see the robot in the background, it's not being used. This is his unassisted abilities. We'll see use of robot in a second. In the big picture, he's relatively young, was very healthy, and is motivated to recover. So why did the best possible treatment, he got treated in Austin in a really good hospital. Why did that not lead to full recovery? Could technology, specifically robots, help with the therapy that results in better and faster recovery? That's really what we are after. These questions are that motivate my work, and I'm going to show you a robot that we built and then how far we have gotten on that case. Okay, this is not pandering. Neville Hogan has influenced my work. I show this in all my talks, not just at MIT. Robots have been used for, especially starting with Neville's work, robots have been used for human-robot interaction. We could begin to then think about robots being outside of industry setting for a variety of applications, including therapy. One of the early motivations for developing rehab robot was that robot could increase dosage and take physical burden away from the therapist. This makes sense, right? In addition, robots possess more capabilities, including quantitative data gathering, syncing with other technology, and special features, which is tunable assistant to encourage patient engagement. And we'll talk about a bit more of that as we go forward. This kind of starts to fall under that changing of internal state that I've been talking about. So where are we in sort of the picture of rehab robots? Initially, the robots started as planar machines. It's one you see here, right, built at MIT. Since I began, designs of robots, rehab robots have been improving, and many exciting advances in design and control have happened. Still, there are some limitations, and that's what our design went after. In an exciting way, researchers have shown that robots are capable of delivering therapy. Some of the robots have been tested on stroke patients, including the Manus robot, which probably did the most tests as far as I can notice. And the results show that recovery after robot is comparable to recovery after high dosage of conventional therapy. This is promising because studies confirm that robots have been safe and effective in delivering complex therapy. Robots took the physical labor off of therapist's hand, and robots increased the dosage. Now, my work builds upon these early systems and hopes to take it to the next level. I have done this by tackling limitations of system on the design side and head-on tackling the challenge of how do we affect the internal state to cause the best recovery possible. So what were the limitations that we aim to tackle? First is that very few robots had 3D movement support. As that, you can imagine, limits what types of therapy we can give. Robots typically not designed to train both sides of the body. This may seem a bit counterintuitive because stroke affects only one side, but neuroscientific studies have shown that bimanual training may have a positive impact on the recovery process. So we wanted to tackle bimanual training. And this is an important point, which is although some robots had impedance control and torque control, which we'll talk about details in a second, overall, there was a lack for adjusting the interactions in a broader way. So what we would like to do is engage patients. We don't want to do the job of the person. We want to engage them so that we train them. Their brain recovery happens, their internal state changes, new neural growth happens. So our robotics challenge is that we want to create situations so that people learn and robot goes away and they have the function back. So for to be able to do that, we need a lot of ability to change the interactions, and we didn't have that before. We designed and built Harmony Exoskeleton that addresses many of these unmet needs. And I could say that this is one of the most advanced robots for upper body rehabilitation. We did this by first developing our own manufacturing system. We dove deep and we did key technological innovations in actuation and control for fast loop, but also accurate torque control, which is at the heart of achieving this wide variety of interactions. Neville's work had shown that we must be able to control forces transmitted by the robot to the body, and it's okay to sacrifice high precision in position control. And this is divergent from most of the robotic system. We take kind of the torque control as our higher priority than precision. We're talking about sort of micro or millimeter level precision. We don't have that, right? So that is human interaction and ability to be on that spectrum of challenging the person and assisting the person is where we decided to land. So then, and then we also, we have mechanisms to get the shoulder motion. I will tell you a bit more about that in a second. We have ability to fit to wide range of participant sizes, where we design our own mechanisms for attaching and detaching so that we can do that quickly for a wide variety of patients. We have dozens and dozens of sensors to measure position and torque, so on and so forth. Our own sort of firmware, our own hardware at the lower level, and our own software and control. Overall, then, this is a special tool, in my opinion, for probing this interaction and modulation of internal state. These are the types of questions now we can answer with that. Before we dive into that, I want to show you a few more technological details I thought that will be of interest to this crowd. But let's start with a video of the robot itself. You're going to see the robot built in collaboration with my startup and my lab. All the initial innovations occurred in my lab. We're going to see a healthy individual in this robot. And first, we'll show sizing adjustment. Then we're going to see donning and doffing. Then we're going to see what we call the weight support mode, where the person does not feel weight of the robot or their own arms. Then you will see a couple of examples of functional training, a few more pre-programmed motions. And finally, you will see an exciting bimanual sync mode, which we'll show now, and we'll come back to it again. This is the bimanual sync mode that I was talking about. Cool. OK. Let's dive just a few steps deep, dive deep in at least a few different directions. One is the shoulder motion. Human arm is not directly connected to the human trunk. It is connected through the scapula motion. We all know that. We can feel it. A lot of us live with shoulder pain, and then you got to kind of learn it in a way during your therapy, so on and so forth. For stroke patients, OK, so before we go there, let's think about that. This is called scapulohumeral rhythm. As its video shows, as you lift your arm, your scapula has to move, and we have this all kinds of very interesting musculature around that floating bone, right? In case of stroke patients, what happens is that we have to be super careful as we are moving their arm because they have a lot of shoulder issues where the shoulder may pop out because the muscles are not strong, and they don't have that coordination, healthy coordination. And many times they may not feel kind of the sensation if you move in an unnatural way. So we need to be extremely careful in moving in a natural way and matching to the person's ability. This was our first mechanical challenge. We designed a mechanism by defining 5 degrees of freedom around the shoulder. This is 2 more than what you typically would think, right? You think shoulder or hip as ball socket joint and 3 degrees of freedom. This is more than that because of that scapula we need to be careful about. So we have these additional degrees of freedom that kinematically could be actuated. And this is the kinematics. We need this because you also don't want robot to collide with its own body or collide with your head, so on and so forth, right? So we designed this system. And let's see this in action a bit more closely. You saw one video. I'm going to show you one more video. It's a short video with my former student, Anna, who is in the robot. In this case, robot is passively following her. Okay, she's moving, and robot is in zero torque mode. And this is to highlight how the robot controls its own joints to be able to match with the motion from her case. With this, we did some testing with healthy individuals, and we see that we are able to achieve full range of motion with quote-unquote proper coordination. And this shown by the gray dot showing the wrist position and orange dot showing that glenohumeral joint position, confirming that the right coordination was achieved. So if you don't have this coordination, if you don't have this joint, that means either your range of motion is limited, or you have the range of motion, but you have kind of parasitic forces on your shoulder. You don't want either. Let's dive a little bit deep. I couldn't show a talk without few block diagrams of control. This is the baseline controller for the robot that has, as you see, low-level torque control with SEAs, compensation for robot's own dynamics, feed-forward control to achieve the scapulohumeral rhythm control. This is not, although we have, so we introduce additional mechanical degrees of freedom and couple them through software control, right? And that's that component. And then we can add task level control, which is weight support, assistance, or even resistance. So you see, this is the baseline controller for what you saw in that sort of early videos so far. With this type of control, then you can do impedance control based torque tracking. This is example from one of the early studies on healthy individual. This graph is showing x-axis is time, y-axis is displacement. Think of displacement at the wrist joint, for example. And the robot is, the dotted lines that you can barely see are the desired positions. And you want a robot to go through up and down cyclical motion, right? So it does good tracking, that's good. And then as you do bumps to the robot, and you see it in some of the labs here, because you guys have a number of torque control robot labs, so this is not new for you, which is that as you bump into the robot has graceful recovery, and you can tune how quickly it comes back based on the gains of the robot. So, with this in mind, you can see back to Everell. Remember, he couldn't really move his arm. And now this is sort of baseline therapy for him. And we're going to go well beyond this through some of our theories, but this is, I had to show this to you, is like this is what therapy could look like for you, which is say that cyclical motion, we move him. This is great sort of as a table setting in this case. Right? This is predefined motion that were suggested by therapists to us. So kind of we define the motion based on the principles that therapists gave us. I think that's good. I want to show you then bilateral sync in slightly, a one level deeper. In this case, if you have that of control, then you can say that one side of the body, we can just do it in zero torque mode with the control diagram I showed, and the person can move relatively freely. We're compensating for robot's weight and dynamics, so on and so forth. And then you can use those trajectories as input for what you may call affected side, and then do impedance control, trajectory tracking on the other side. And we have fairly fast control loop, so with that you can achieve performance like this. In this case, you have Anna, my former student. in the robot, and my other student Kia in the robot as well. And what you're seeing is Anna's left side is in control, and her right side is going along for the ride. And then we just wanted to see that clearly. You can see now this is a bilateral sync control. This is an example where what therapy world calls mirror training, right? So really, they do training with mirror in front, ask people to move their healthy side, see that in the mirror, and then kind of affected side is also attempted to be moved. Okay. Let's see Avril in this robot. This is him. We did a study with a bunch of patients. Avril was one of the patients. Mostly we did that passive motion that you saw earlier. That was our main study. But just for fun, some of the participants, we offer them to go in this bimanual control mode. This is, next two are my favorite videos because this is day one of bilateral sync. We just said, get into the robot, do what you want to do, right? So you're going to see him in the robot, and then we'll take a pause, and I want to actually maybe take a chance to, if I'm allowed, to take a few questions right here as well. Let's first see. OK, I'm going to show one more video, but I want to kind of remind you, this is the control he has, right? And then he's not able to lift his arm. OK, now second video, he's going to do a few more fun things. This is just same session, just a few minutes later. One of the things he's going to do is stretch his shoulder that he just couldn't do on his own. That's one of the things he really appreciated. He found himself in that position and proceeded to do robot dance because he's the guy, kind of guy he is. OK, thoughts or questions, maybe one or two, just so that I'm not just talking the whole time. Anybody has? Yes.
Strikes me that ultimately make this waterproof because swimming would be an amazing therapy for this guy.
Yeah. Interestingly, our robot in zero torque mode feels like you are underwater. Right? There's a bit of that. But you think about gravity taking off and smooth. Yeah.
My father is Parkinson's, and when I take him swimming, he's like, gravity is gone. I'm so happy. And
that is one of the principles I'm actually going to show you in our change of internal state. First, and
support the spine also?
no, we all not actively. We are on the stand, and sometimes we therapists decide to strap people, and that's how we. So it's not elegant solution, but that's how we do it. Yeah.
So for every patient, is the kind of therapy, is it same or is it different? And if it is different, how do you, so do you always train them by using a, like a healthy person and then pass it to the person who need that, or how do you manage all this? Like,
in this, our early attempts, it is focused on trajectory following with this impedance control as underlying. When we could, given a trajectory, then we can do a few fun things, but not a lot, where we could say how much assistance we give or let them finish, and then we add assistance. You know, there are principles in rehab world of assist as needed. error, augmentation, so on and so we did that. But the trajectory we could adjust for each person based on their range of motion and where they were, so on and so forth. But the bigger principle was kind of constant of like either go along the trajectory. That's in the bigger therapy picture as just a sliver of what we can do, right? Fixed trajectory and then do some fun robot stuff on that trajectory. We need to be able to do more, and I don't have good answers yet for it, which is actually what is the disability they have and how do we design even which zone of therapy? Is it trajectory following or something else? Is it gravity compensation or really completely new and different things is what we will have to get to. And we as a field, I don't think we are there. Right? That will depend on knowing that person, their recovery potential, right? How old they are. If they're younger, actually their potential goes up, like it or not. If we are early in the recovery stage, we do something. If they're later, we do something else. So that's the type of broader customization I'm envisioning, but we are nowhere close to that. We do customization, but in that narrow band. Does that make sense? Yeah. Okay, cool. In the interest of time, let's keep moving. Okay, so we can go in again. I can talk about that. This is years of work. I thought I will just show a few highlights on. I think overall we feel very good with our system. It could have other features. It could be, compliance range could be larger, so on and so forth. But we have a very good system, kind of a sandbox to play with. And then I want to tell you some ideas about how to affect the internal state. What are we thinking about? What's currently missing in the bigger picture, if I could say that, is none of the current robot approaches directly focus on changing of the input signal. We have been focusing on, as a field, more on how to move the behavior, but the internal state is how does brain send the muscle control command, and if that's wrong, then how do we actually change and probe that? And broadly speaking, even in neuroscience and clinical world, we don't have kind of direct solution. We say that's what we copy and I write the code for it, right? It's not as simple as that. Even there, we don't know. We don't have good understanding of how the stroke affects you and what is the recovery trajectory and what therapy motion I should do for that person. So we are now in the business of actually exploring that, right? We are not in the business of sort of take some clinicians and quote unquote automation. We are actually collaborators with clinicians to understand, clinical and scientists to understand that process itself. And I want to talk about two ideas. This is a big open field. One of the ideas is to target, two big dominant impairments that happen after stroke. Each person's stroke recovery is different. So many things can happen, and stroke is actually not one thing. It depends on where it happened, what type of stroke, so on and so forth. But broadly speaking, people have muscle weakness, meaning that they just don't have strength in their muscles to move. And second is they have what's called flexor synergy. I have had very interesting conversation with many folks around synergy. And this is synergy is usually considered a positive word, simplifies control problem, and so on and so forth. In this case, it is not a good situation. People have this synergistic motion that limit them from being able to complete coordinated, elegant actions. In this case, one of the synergies is called flexor synergy, which is as you lift your shoulder, your whole arm flexes all the way to your fingers, right? And that's problematic, right? You can't go grab a cup. Many kind of limitations have come out of that. So then we started to think about, instead of taking the robot through this fixed trajectory and then doing clever things on that trajectory, or rather, with that, are we targeting this? And we quickly realized we're not targeting those impairments. We are indirectly maybe, but we're not taking it head on, right? So we decided to try to redesign our controllers to be able to target this, or build new behaviors to target these types of impairments. I'll show you some early ideas on this. This is still, in sort of my career, this is the last 1 or 2 years of work, so it's still new. We're still sort of, I would say, in the big picture, just starting to see some light in here, but lots to do in this area. So the principle for improving muscle weakness is gradually reduce support against gravity. Okay, so our robot is torque control. At each joint, we have all these features. So then we can apply counterbalancing torque. And then we can use tunable anti-gravity force field to gradually reduce support. When I say gradually, I mean maybe during one session or over multiple weeks, right? As you see progress, that is all still being decided. It will depend on each person. And other idea is that other idea is to make synergistic movements energetically costly. So let people move, but make motion around the synergy components energetically costly by creating tunable viscous field. And these are fields created by our low-level torque control. Few more control diagram. The details are not super important, maybe very interesting for some of you. But at a high level, we can apply wrenches at the joints. And then we have additional kind of task space. We have this partial weight support. And it's tunable, right? You can start with 100% we saw in earlier videos, and then we sort of updated it so that we can have different levels of gravity support. And few other people with planar robots have shown that this is promising approach. And one of the ideas is that as soon as you change that gravity support over time, people's range, if when they have larger gravity support, they have larger range of motion, right? That means one idea is that underlying they have good control, but that's dominated by a need to work against gravity. So that we were trying to elucidate that, and then slowly adding gravity to see if they can get better, right? That's the idea here. But people hadn't done this in 3D, so this is the first instance of that. So to understand this, we haven't done any stroke testing on this, but first whether this idea actually is effective, we did testing with healthy individuals, and our idea was is that we want to see if support level changes affects participants' effort, right? So then at least that's kind of the first check on this. So we're testing with 14 participants. We recorded joint angles and surface EMG. Our metric was effort and kinematics. We wanted the same kinematics, but effort to be changing. This is my student Ana Oliveira's work. She's in the robot. She has this amazing ability to be kind of fake participant and control the robot at the same time, which is, I don't know how she learned that. But she wasn't a participant. This is just for illustrative purposes. So this is a static task to go from one point to another. And this is, I believe, sped up at twice the speed. Okay, so we let people do that, right? And it's under different gravity support conditions. And we recorded the kinematics and the surface EMG. Those who may not know EMG is electromyography from your muscles. It's an indicator of your muscle effort, if you will, right? And this is a dynamic task where she created this task where we asked people to kind of go through their wide range of motion. Visually, they were given this feedback is to just go paint in that 3D space as much as possible at their desires, their chosen speed. Okay, so what do we want to see, and you will see some results in a plot, is that as gravity support goes down, your muscle effort should go up, right? That then shows we have effect, like we actually have a knob that affects something on the muscle. And luckily, we do see that. Okay, in this plot, I'm sorry if the text is small. In this plot, x-axis is the amount of gravity support in static conditions, and y-axis is our own measure of muscle activity, indicator of effort. And you see that in both static and dynamic conditions, the muscle activity increases, or the muscle activity decreases as the gravity support goes up. And I took that as like first instantiation as we got desirable changes in muscle activation based on what we did with the robot, right? This is sort of starting to think of in a maybe bigger picture, simplistic way, but we have some sign of life that we can change muscle activations. And we didn't tell people that, right? We just sort of let them do some tasks, and we had the desired effect. Let's think of something a bit more interesting, where synergy-based control, and we created force field that makes certain coordinations energetically costly, as I mentioned a few minutes earlier. So let's take an example of not the flexor synergy, because that was, we didn't want to start with that, but another type of synergy that involves shoulder and elbow joint. right? So it's a little bit different than stroke synergy, but this is an illustrative example. So I want to explain this idea first, show a little bit of math, and then show results. So imagine that this is a velocity space with shoulder flexion and elbow flexion. And we define that, just it's our choice, we define that we don't want people to be in that zone. Okay, that's our unwanted coordinations. Imagine that this is the unwanted stroke coordination, right? We want people to be away from that. One way is that we just grab their hand and say, don't go there. Let's just really stop them, right? We're not doing that. We want them to move, but then make that energetically costly to see, and in this case, to see if it is energetically costly, right? The longer term would be if that has the effect that people from stroke recover. We're not there yet. So then, just for safety, you add some dead zone. We define these vectors, right? And then we say that if they are outside of this, great, apply no torque. But if they are in that zone, then you need to apply torques, sort of energy-based viscoelastic field. And then, and it's tunable, where you have these lambdas where you can say kind of what is the strength of that field, as you can imagine, that's the control level. And this is what the energy field will look like, something like that. So it will take you out of, or it will apply viscoelastic forces on you. And then in control diagram, that becomes another term on top of sort of, that's our whole enchilada in this case. We did testing with 40 healthy participants, measured joint angles and surface EMG. We measured, our metrics were effort and kinematics. I guess I should have shown this EMG picture in the earlier slide. This is what those who don't know EMG sensors look like. You can slap them on. This is off the shelf from Delsis, which is Boston based. You attach them on the muscle belly, and you get signal of the effort. It's sort of standard in many labs like my lab. Okay, and this was our task. So this is, for the sake of argument here, Anna is in the robot again, and this is our targeted coordination. We don't want people, we want to make this energetically costly, right? And then we want to see if they apply, if they made it. And for the sake of comparison, we said this is non-target. This is great. Robot does not apply viscous field in this case, right? We wanted to do comparison. And we can change the strength of that viscous field. I think there is a bit more on her. Yeah, and it's kind of, we give visual feedback. This was the motion, and we did it at various gains level, right? Okay, luckily, we see that as we think about various muscle group in the targeted times, the muscle effort for all the groups, y-axis is a measure of muscle effort, x-axis is different muscle groups where we attach these sensors, and we see that the targeted effort was higher because they did respond to that viscous field. And we see, everywhere that's true, and it's tunable in the sense that as we increase the strength of that field, it becomes more viscous, and then we have this ability to sort of tunable viscous resistance, right? Then I think of this as, okay, it's another evidence that desirable changes happens in muscle activation. So we are now, in my opinion, starting to target what's the input. That's where the problem is. Although we see the behavior, we are on the behavior output side, we are able to affect the input side. So in summary, we have tunable anti-gravity force field, tunable viscous field, and we are able to achieve desirable changes in muscle activations. I want to tell you sort of briefly some of the ongoing research directions. We're building upon that. One of the directions, by the way, we're taking is using our robot to understand state of stroke overall. We are able to collect variety of data. We can put people through variety of kind of situations, including proprioception data, meaning that do people know where their arm is? Because that's one of the key measures of if they can control it. With our robot, we can create very interesting testing of that. You can, of course, collect motion data and motion quality data, so on and so forth. I'm working with John Krakauer at Johns Hopkins on these kind of metrics and measures. I'm working with Brittany Muir in Seattle on applying this flexor synergy idea in very early stages of stroke. We didn't talk too much about stroke stages, but overall idea is that the earlier you can treat, even days after stroke, if you can bring robot in that stage, might have the most promising results. And typically, all of our testing sort of all over the world has been on 6 months later or 3 months later. So we are trying to bring the robot very early, like 2 days after stroke, so on and so forth. I showed you this bimanual control a second ago. We don't need this to show this video, but I want to show that I'm working with Jose Milan. We're developing a brand new approach where training at the distal level is mediated by state of the brain in a closed loop and continuous manner. So now we're getting at brain data to see if we can do bimanual control such that the person not only gets to move their robot with their healthy side, but there's a gate. They have to think about moving their healthy side. Even though they can't move it, we can record that, and the affected side assistance is mediated by the state of the brain. And the idea is that this platform will be first of its kind for probing interactions of preparatory descending signals, that is, people through BMI system, and ascending neural signal generated by the robot-mediated movements, both kindled and amplified by this bilateral therapy approach. I just said that already, but I want to show this video. I think this is kind of really new results, or new at least video. Here what you're going to see, before I play it, is we're going to see a healthy individual. They are controlling the robot through their BMI signal. So they are asked to start the motion and end the motion. I don't have time to go through all the detail, but let's just play the video here. So the green light, if you can barely see, says we got their signal and robot starts moving. And then the red light indicates to them, send a stop signal. And that's when the robot starts to move, right? It may seem like nothing. This is, to me, so kind of mind-blowing for my own sake. We didn't think that we could get robot to do control with their brain imagery, right? There has been some work done with some other robot control, but wearing the exoskeleton and controlling your own body through brain signal, I think, is pretty amazing. And just to kind of make that point in another way, you're going to see him outside of the robot and controlling. This is what was happening. Right. Cool. I think in the interest of time, I'm going to skip this and just show you this video where we had people playing interesting dynamics game, and we changed the control of the robot to get them to do dynamical tasks in this virtual reality setting. So we could use the robot to change the dynamical conditions. In this case, healthy individuals, because we wanted to understand motor behavior in this case. This is in collaboration with a computer scientist doing curriculum learning work and a neuroscientist at Johns Hopkins University. I want to show 2 more videos. Okay, this video, it's older video, but I really love it because here you're going to see another robot. In this case, you're going to see a spinal cord injury patient whose hand motions are super limited. You can see his left hand. His right hand is the same way. This is spinal cord injury, so both sides are affected, unfortunately. He couldn't move, grab stuff, but with our exoskeleton, he could do that. But the interesting part is that he is generating his own control signal. We have attached his EMG signals to his body, to his forearm, to the relevant muscles, and we just let the robot be controlled by those signals. Again, this is not pre-programmed control, but direct control with input from the user. This is one example we tested and shown that this approach works for many patients and many dexterous manipulation situations. We are also looking at harmony in other situations. This is thinking about telemanipulation control, where we can use the robot as an input device for controlling other output systems. So this is outside of medical application. This is thinking about telecontrol of complex systems. Right? And a startup is spun out, you see that logo there, and the goal there is then using this robot to control a complex robot. These folks have already achieved. This is my colleagues here showing telecontrol of a box unloading situation, where a lot of times they could be done autonomously, but many times automation may not work. So a person could remotely kind of beam in to control this type of robot. Cool. So with that, I'm going to stop. Thank you so much for listening to me. I look forward to taking on a few questions. Yeah.
So questions from the audience?
Thanks, Ashish. That was a tour de force. One of the things I'm curious about is muscle weakness and abnormal synergies. Are they related?
That's a very good question. I don't know. I think typically when clinicians or neuroscientists, John Krakauer talks to me, he thinks of different stages. He thinks of, he tells me about flaccidity, where you just have nothing, to some strength coming back. But as soon as that strength comes back, it may take a while to strength to come back, but as soon as you have the strength back, it is in this flexion synergy fashion. So I don't know if there couldn't be the demarcation. One must be related to that, but I think we are, at least at this point, thinking about targeting those separately. But yeah, I don't know from the neuroscientist science perspective answer to that. Do you have any thoughts on that, or?
Well, my sense is that, for example, if I have extensor weakness due to disruption of one of the corticospinal or rubrospinal tracts, then if I try to do this sort of thing, I may wind up with insufficient ability to
counteract.
To counteract.
Counteract that, yeah.
So, so there could be some relation, but I don't know the details.
Yeah. So yeah, that could be neural misfiring, or could be just weakness from that you don't have ability to.
And then you may learn the inappropriate coordination.
Yeah.
Thank you, Ashish. Great presentation. I have two questions. My first is a curiosity. So, I wonder, what's your opinion about end effector rehabilitative robots? So you have shown us exoskeletons, but there's also the other side of the medal. And so what do you think about that?
Yeah, I like those as well. I think this is such an open, challenging problem. We should all, I would say. I think they could create, first, wearable robots create a lot of challenges, encumbrance, limitation. I think therapists talk to us about, hey, could you get it so that people are able to stand and work in the kitchen setting, right? They are healthy. Everell, for example, can stand on his own, walk around. So why am I strapping him into a smaller fixed situation? So end effector could create that, right? You could have robot coming out of kitchen setting, and they are able to do that. I think, and they may have other ways to affect the muscle activation. I think we just haven't been playing in that field. We are more focused on how to get joint by joint trajectory tracking so much, and then we debate end effector versus exoskeleton. But if you think about, I haven't seen many examples of how end effectors might have role to play in terms of activating certain muscle patterns that we really want to target. So there might be areas in that. Yeah, I'm not opposed to it at all. Yeah.
Great. And the other question I had is that with exoskeletons, at least in my experience, you have the problem of the interaction between the arm and, for instance, for upper limb and the exoskeleton. So how do you try to minimize the problem of friction or slipping that you have?
Yeah. So we spent a lot of time in lab, but also through that startup is on that cuff design and cuff attachment. So I think we're still in the passive area. I've seen some examples of active design that can be even more interesting, where you have, that as you're shape changes and volume changes, how do we adjust to that? We are not in that zone, but we just have, first of all, we design multiple sets of cuffs, so the different sizes, we just slip in and out. And the other thing is that because of our kinematics in other places, we don't have a lot of slip forces, not as much. I think there's some singularities where it does show up quite a bit and then it starts to slip. But outside of those certain zones, our shoulder mechanism ensures that you don't have a lot of yanking on your arm in that case. So it's less, but it's still, we are dealing with people with wide variety of situations in that case. So I think some other active situation, I don't know if you've seen that, but there's some active mechanisms that are pretty promising.
Thank you.
Yeah.
So we'll take the last question.
Sorry, the ongoing research project you shown about BMI,
Yeah.
it was really interesting. So
Yeah.
what I understood that you are taking an EEG from
Let
a
me
person.
just go to that. I'm listening, yeah.
Yes, so you're taking an EEG from a person, and then the output here is how, like, maybe the kinematics or the joint velocities of the robot manipulation. So my question is that, like, the earlier videos you were showing where people with disabilities were using the machines. So can we go, like, have you thought of going to the inverse, like when they're moving their arm, how the EEG or how the brain signals are happening in the in their brain, whether that is actually affecting the part of the brain you're trying to affect? Because since there are some, I think Meta has also some like similar research on like creating brain images and stuff.
First, I would say with BMI, we don't have that granularity with this type of BMI. Just to probe at your question, I would tell you that what we're doing is much simpler than that, right? So what we are not, so when we're doing bimanual training, we're getting kinematics from this side and feeding that to this, right? We don't get that kind of kinematics from brain signal. We have no hope of that, right? So what we get, though, is some broader, more abstract signal of starting to move, right? So they imagine to move, and we have signal. That's what my colleague Jose Milan's expertise is. You have kind of initiation signal and stopping signal. Even stopping signal is novelty, right? So I think for that, I think we confirm that with healthy. I don't think we'll try that with stroke. When we first start to work with stroke patients, we will actually doing what you are suggesting, which is kind of, is there mapping between their motion and the brain signal? But what's actually more challenging is, are they able to generate right signal through thinking about is motor imagery? And is that kind of precise enough so that it happens every time they think about it? It's very hard. Our success rate is not that high even in this situation. So what we are doing in this case, just to clarify, is we're still getting kinematics. Our idea is to still get kinematics from the healthy side, but use the BMI as a gate before we can help. Like, you must think about moving. And when we say think about moving, is just on and off in a way, or you want to initiate. And the kinematics is the one that dictates the assistance. Yeah.
Great. So let's thank the speaker once again.
Thank you so much. Thank you.